Welcome back. We're going to look at some examples of creating centers of mass for one-dimensional objects. Now, we haven't done too much work with one dimension, but you'll see that we will quickly move into 2 and then 3 dimensions from this idea. So, let's start off with a classic example of trying to find the density of an object that has been fused from 2 different alloys. This is often done when you are working in metallurgy and you take 2 pieces and you just fuse them together. Where's the balance point between those 2 pieces? You also run into this when you're playing with Legos and you put two structures together and you want to find where's the balance of it. Okay, so as a kid, perhaps you remember doing that. We're going to look at specifically finding the center of mass for an object, not an object, a long rod with density rho of x defined. The piecewise function, let's start with a piecewise constant function. 1 for x between 0 and 1/3 of the length, and then 4 between that third all the way up to 1. So let's talk about that. Length being 1, that's our final length. And right at the intersection, we don't really have the density defined. It's not yet. We have to be more careful about that. So we're going to say that it's on this side. For integration, we don't necessarily worry about what happens at a particular point. We're integrating over an interval. So it's okay to have issues like this, discontinuities. First, we add up our mass. We know it's the integral of our density function, but our density function from 0 to 1, the whole length, our density function is defined differently. So let's integrate over the separate pieces. 0 to 1/3, we have our density function of 1. And then from 1/3 up to 1, we have our density function of 4. Now, because these are integrals of constants, we can integrate them really nicely. We end up just getting 1 times the difference. So that's 1 times 1/3. And then 4 times the difference in that length. 4 times 2/3. And if we add those together, we get 1/3 plus 8/3, which is 9/3, also known as 3. So we have our mass of the object. We want to know what the center of mass is, and we just have one variable, so let's look at the moment mx bar. That's the integral of x, rho of x dx, over the interval from 0 to 1, but again, we want to break it up into 2 pieces. So we have our integral from 0 to 1/3, and we throw in x here, plus the integral from 1/3 to 1 of 4x dx. I'm going to integrate those 2 pieces separately and then add them together, but they are very similar. We have an x squared over 2 from 0 to 1/3. And then a 4x squared over 2 from 1/3 to 1. Factoring out a common 1/2, plugging in our limits. Factoring a 4 out of those 2 pieces, plugging in our limits. have, do a little bit of arithmetic here, 1 minus 1/9 is 8/9. So we have 32/9 from that section, and we add 1/9 to it, we get 33/9. So we get we can reduce that down by dividing out by 3, giving us 11 over 6. So that is our moment. We then find our center of mass by taking the moment divided by our mass. So 11/6 divided by 3 gives us 11/18. Now, how does that compare to the rod? Let me go back up to the top and draw this out. So in our fused rod, we notice that the density of the larger piece is also significantly larger. And if we look at half of that larger piece, that's at the 2/3 spot. If we ignored this first piece, that would be the center. Constant density, the center of this second piece would be at 2/3. And if we add in a chunk that is light, we will pull the center of mass slightly to the left. And the value we get is right there. 11/18 is just shy of 12/18, and 12/18 is 2/3. So there we go. There is the balance point for our fused rod. We can estimate where it is visually just by thinking about the pieces. The larger or the more massive piece is going to center the entire center of mass, shifted slightly by a little bit of mass added on the end here. Okay, let's now look at a more complicated 1D example that leads us into 2 dimensions. For our second example, we're going to look at a one-dimensional wire instead of a rod, but we're going to look at it being bent and find the center of mass in 2-dimensional space of that bent wire. Okay, so let's first visualize this object. Semicircle would mean something like that. And those are the endpoints of it. Now, to look at this object in 2 dimensions, we're going to have to give it some thickness, like we gave the rod some thickness to think about it. Even though it is we're going to be treating it as a one-dimensional object, we have to give it some thickness to place it in 2 dimensions. And I'm going to choose to give it the same thickness radially. That does mean that there was some compression going on when I took the long wire and I bent it into this arc, but it allows me to work in polar coordinates. And after I evaluate this 2-dimensional center of mass, I'm going to let delta R go to 0 and trim that thickness down toward 0, so that I'm just looking at a 1-dimensional object in 2 dimensions. Now we're looking at center of mass of a thin wire, and I'm going to add that we are working with it along that says line wire, I apologize. A thin wire, let's treat that. With and we'll add that it has constant density. So that our center of mass is really just a centroid calculation. How do I get that? Well, if I think of my center of mass in terms of a constant density times x average divided by a constant density times the area, then I can cancel out those constant densities, leaving me with the x average over the, I'm sorry. Let me try that again. When density is constant, center of mass equals centroid. What that means is that my x bar, being the ratio of my moment over mass, can be thought of as the integral of some constant density times x. I'll rewrite that in order. X times some constant density, dx, divided by the integral of that constant density, dx. And those constant densities can be factored out. So it goes from A to B, A to B, A to B, A to B. And then once we factor them out, we can cancel it to find x average. The integral of x over the interval divided by the interval length. In a similar way, if we swap out these single integrals for double integrals, we can look at the x bar component of the center of mass. Same constant density, factor it out, and now we have the double integral of x dx divided by the area. And that will still give us the average x. We can do the same thing for y bar and y average. So that is the idea we're going to utilize. The other helpful thing is to think about this mass in terms of this little area strip. So I want to find that first. I'll just look at the area, find the area. To work in polar, we have to pay the cost. The r variable goes from 1 up to 1 plus delta r. And then theta goes from 0 to pi. We can integrate in terms of theta first, since there's no theta function given, and then integrate to give us r squared over 2 evaluated from 1 to 1 plus delta r. And this gives us the difference of two squares. Now it seems kind of silly to write 1 as 1 squared, but it helps us remember that we have a way of factoring a difference of squares. So I'm going to write this down the corner. Area equals, and I'm going to look at first the difference of this a times minus that b, so 1 plus r delta r minus 1 gives us pi delta r divided by 2, and the other factor is 1 plus delta r plus 1, which is 2 plus delta r. Now it may seem like we could take the limit as delta r goes to 0 here, but then our area is gone. So let's hold that off just a moment and go to find out what the integral of x dx is, the x moment. And then we'll take the ratio of the two and let delta r go to 0 at the end. Now, the double integral of x dA can be set up as 0 to pi, 1 to 1 plus delta r again, x converted into r cosine of theta, and then dA converted into r dr d theta, paying the Jacobian cost. Here, we separate into two integrals. For theta, and then for r. And let's integrate in theta first. Get a cosine goes back to positive sine, evaluated from 0 to pi, and then we integrate in terms of r cubed over 3, 1 goes delta. Sorry, backwards. Okay. Now, you may have noticed something strange here. When I integrated cosine, I got a function that is 0 at the two endpoints. Sine of pi is 0, and sine of 0 is 0, which means my moment for x is 0, or the x average is 0. Okay? Well, how do I know that? Well, once I divide by the area, I get 0 again. So I know the x average is 0. Should I have known that from the beginning? Well, from my drawing, I created this thin rainbow shape that is symmetric about the y-axis. And if it's symmetric about the y-axis, it has symmetry in the x direction. Symmetry. And so it should be balanced. And so x average, x bar, should be 0 right there. Okay. Can we interpret that from our drawing? Yes, because we have constant density, the geometric center will be the coordinate for the geometric center, the centroid, will be the same as the coordinate for the center of mass. So we know x bar is 0 because of x average, but if we forget, we can always go through the calculations and find it out by integration. So let me now look at the integral for y. From my drawing, it doesn't have symmetry around the x-axis or around any x line. So I expect to have a non-zero value. Now when I integrate sine, I get a minus cosine. And that leads me to minus a negative 1 plus 1, plugging in pi for cosine, or for theta. And then a third times 1 plus delta r cubed. Now I have a difference of cubes. Well, remember how we had a difference of squares before? And that factor is a minus b times a plus b. Well, this actually works for any difference of powers. So in our case, well, what do I mean by it works? Well, what do we have? Well, we can always factor out the difference of the two values. And what's left over is a sum of powers of the pieces, decreasing in A, powers of A, and increasing in powers of B. So here we have A to the first, A to the 0, B to the 0, B to the first, giving us A plus B. In the second case, we step down from A cubed to A squared, and then to A, and then to 1. Whereas B steps up from B to the 0 to B to the first to B squared. So that pattern is preserved for any difference of A to N, and in fact, it's in the front flap of your calc book. So let's use that idea to write out first the difference, delta r, and then the other pieces. we should have a squared plus ab plus b. But b in this case is just 1. So we get a squared plus a plus 1. Okay. So now let's combine this idea to find our y average. Take the limit as delta r goes to 0 of r2 delta r thirds times 1 plus delta r squared plus 1 plus delta r plus 1 divided by pi delta r over 2 times 2 plus delta r. Okay, so first and most importantly, we need to cancel out the delta r's before we let it go to 0. But after we let it go to 0, but after we cancel those out, we can let delta r go to 0 in each of these pieces, leaving us with 2 times 2/3 times 1 plus 1 plus 1 times 3 divided by pi halves of 2. Canceling out. We get 2 over pi, which means our x bar and y bar, the same as our x average and y average, are 0 and 2 over pi. And to visualize that, you can approximate pi as a little bit over 3. And so 2 over pi dividing by a little bit more than 3 is slightly lower than 2/3. So right there, just slightly lower than 2/3 is where the center of mass is in space of this one-dimensional wire now that it's been bent into a semicircle.